This is video 53 in our series on tensor calculus. In this video, we'll introduce and analyze a differential operation known as the curl. The curl is an operation defined by the expression you see here. Now, it looks a great deal like the cross product that we talked about in the previous video. The difference is, of course, that the cross product involved the product of two vectors in these positions combined with the Levi-Civita symbol to produce a third vector here. This time we have only a single vector that is operated on by the covariant derivative operation right there. Now, we know we have a tensor here because the covariant derivative of a vector is a vector, or a tensor, and we know that the Levi-Civita symbol is a tensor, so this is a tensor product. And as with the cross product, there's only one free index of I. Indexes j and k are dummy indexes. So what we have here is a tensor equation, and it has a rank of 1. It is a contravariant vector component. And as with the cross product or any vector component, we can lower the free indexes and swap the positions of the dummy indexes to express it in the alternate form. The curl can be defined either as a contravariant vector component or a covariant vector component. And of course, we can use either form to create a linear combination. We can use the first form, epsilon ijk, times the covariant derivative with respect to j of uk, combined with a covariant basis vector of zi, like this. Or we can use the second form, epsilon ijk in the lower position, times the contravariant derivative of uk, combined with a contravariant basis vector like this. By way of notation, you'll often see this written down this way. Vector v is simply going to be the curl of vector u, or because of the close resemblance of this form with the cross product, you'll often see it expressed this way, the del symbol simply crossed with vector u. Now the form you see here is simple and easy to use in our tensor equations, but similar to what we discovered in the case of the divergence, there's another form of the curl that proves to be more advantageous and more beneficial when it comes to actually evaluating the curl relative to each individual coordinate system. So let's derive that expression next. And to do that, we'll start with our definition. Vi is equal to epsilon ijk, but this time instead of expressing the covariant derivative this way, let's expand it out to its meaning. And to take the covariant derivative of uk, of course we start with the partial derivative of uk with respect to zj. Then, because the index is in the lower position, we're going to need a negative term with the Christoffel symbol and a contraction with u here. So the first index at the bottom is always going to be j here. And then the contraction is going to be between this index and this one, and then k is the one bumped, so it goes right here. So that's the expanded meaning of the covariant derivative. All right, now let's distribute the Levi-Civita symbol into each of these two terms. So we're going to get epsilon ijk times the partial derivative of uk with respect to zj. And then we have the second term, epsilon ijk times gamma m jk times um. Now let's look more closely at this second term. We've got epsilon ijk times gamma m, j, k, u, m. Now we're going to play our old rename and swap game with this. Let's rename index j to k and k to j first. This is just a renaming operation. So j becomes k becomes j. We do the same thing everywhere in the expression. So this is kj times um. So nothing here except renaming the indexes. Now I'm going to swap the position of k and j, and because of the skew symmetry, that means it becomes negative. So this is epsilon ijk. And now I'm going to swap the positions of j and k on our Christoffel symbol. But in this case, the indexes are symmetric, not antisymmetric. So this term is equal to gamma m jk, because, again, swapping these indexes does not change the sign of this factor. And finally, um. Okay, now I think you can see that this expression is the additive inverse of this one. And of course, that means, as always, that the only way that can be true is for this to be equal to 0. In other words, this expression right up here is equal to 0 and can drop out of the equation. Alright, so that leaves us with the fact that our curl, vi, is equal simply to epsilon I jk times the partial derivative of uk with respect to zj. This, then, is our alternate form for the curl. And it should be reasonably obvious that this expression is easier to evaluate than our original definition. And the reason is that it does not involve any Christoffel symbols. Now, it may seem strange to you that such an expression is actually a tensor equation. After all, we made a big deal about the fact that a partial derivative of a vector component is not a tensor. So how is it possible for this to be a tensor equation? Well, the answer to that is that because of the dummy indexes, the expression on the right-hand side will actually expand out to multiple terms. In fact, with the skew symmetry of I, j, and k, there are going to be 6 terms over here that are non-zero. Now, what's happening is that each of those individual terms will not be tensors. However, when they're added together, they will form a tensor relationship. It's another classic example of how we can add non-tensors together to form a tensor. All right, let's move on and derive a couple of really important identities involving the curl. Let's start by evaluating the curl of the gradient. Well, the curl is going to be vi, which is, according to our simplified definition, is epsilon ijk of the partial derivative with respect to zj of the covariant vector component of our object. Well, what is the covariant vector component of the gradient? Well, that's simply the covariant derivative of our function f, or in the case of a scalar function, that's just the partial derivative. So this is going to be the partial of f with respect to zk. And of course, that's going to be equal to epsilon ijk times the second derivative, second partial, of f, first with respect to zk, then with respect to zj. Now, I expect you maybe are able to see what's going on here already. In this term, we have two indexes that are antisymmetric with respect to this first factor. But in this term, j and k are symmetric. We can swap the order of the differentiation without changing the sign or the value of this particular factor. Okay, so that means that this expression has got to be equal to 0. Well, let's just walk through it one more time, so I'm sure you get the idea of how this works, but let's see it one more time just for completeness. We have epsilon ijk k times the second partial of f with respect to zk and zj. Now we'll rename j and k. We'll rename j to k and k to j, so epsilon I kj, second partial of f with respect to zj and zk. Right, and now I'm going to flip the order of the indexes. When I do that on the first term, I've got to change the sign because of the skew symmetry of our Levi-Civita symbol. But when I flip the order of the differentiation, the value of this expression doesn't change. The sign doesn't change, so it remains positive, and it's back into the form of first with respect to zk, then with respect to zj. And now, of course, we have the classic case of this term being equal to its additive inverse, which means that the expression has to be equal to 0. The only way that an expression can be equal to its own additive inverse is if it's equal to 0. And that in turn means that our curl of the gradient of f is equal to 0. Okay, let's try this one. What happens when we find the divergence of the curl? Well, let's go back and use the Voss-Weil formula that we derived back in video 49. So here the divergence of our curl, of our VI component, is going to be equal to 1 over the square root of z times the partial derivative with respect to zi of the square root of z times vi. But instead of vi, let's plug in what we have for the curl. And that's epsilon I jk times the partial derivative of uk with respect to zj. All right, now looking closely here, what is the expression for square root of z times epsilon ijk? Well, using the definition of our Levi-Civita symbol, that's going to be equal to 1 over the square root of z times our permutation symbol like this, and of course the square root of z factors cancel out. This is just equal to e ijk. So we can substitute this expression for the combination of terms right there. But of course e ijk is a constant, which means it can come out of the expression back here, and when combined with this guy is equal to the Levi-Civita symbol epsilon ijk. In other words, we can write it this way. This is now equal to epsilon ijk times the partial derivative with respect to zi of the partial derivative of uk with respect to zj. In other words, this is the second partial derivative of uk with respect to zj and then zi. Well, now I'm sure you see it, that here we have indexes I and j which are antisymmetric in this term, but down here they're symmetric. So when I rename and flip these indexes, the sign will change. When I rename and flip these indexes, the sign doesn't change. So this expression has to be equal to 0. It's as simple as that. This is equal to 0. So that in turn means that our final result is that the divergence of the curl is equal to 0. So again, we have a great example of the power of tensor calculus methods, because we in effect have a one-line proof of the fact that the divergence of the curl of a vector is equal to 0. With that, let me conclude the video with some comments regarding the geometric significance of the curl. Consider a vector field such as the one illustrated here. You can see that the vectors are pointed in generally a clockwise direction like this. Now, the curl is a vector function that quantifies this rotational nature, or the torsion of the field. Think of the field as the flow of some sort of a fluid. If we placed a ball, say, right here in the fluid, then it's going to start rotating in a clockwise direction. The curl is a vector that points in the direction of the axis of the rotation. In this case, it would point into the page. And the magnitude of the curl equates to the speed of the rotation. Now, the fact that the curl of the gradient is 0 is very significant. If the curl is not 0, then the vector field itself cannot be a gradient. I hope you see that. If the vector field were a gradient, then its curl would be 0. So if the curl is not 0, then the vector can't be a gradient. Now, although we're not going to prove it here, the inverse is also true. That is, if the curl is 0, then we know that there is some associated scalar field whose gradient equates to the vector field. Now, to see why this is important, let's consider the case where the vector field is that of force. Force is said to be conservative if the amount of work done to move from one point to another, say from point A here to point B over here, is the same regardless of the path taken. So here you can see that the path matters. If I move from this point A to point B around this way, I'm working against all of these lines of force. If I move in this direction, I'm moving with the lines of force, which means it takes more work for me to go this way than it does to go this way. So with this example, we do not have a conservative force. On the other hand, if the curl were 0, meaning no rotation, then the path wouldn't matter. So when we're dealing with a force field, we start by calculating the curl. If the curl is 0, then we know that the force is conservative, and we can proceed to derive the equivalent underlying scalar function, which in the case of a force field is known as potential energy. Now, this greatly simplifies the nature of the problem because it's a lot easier to work with scalars than vectors. On the other hand, if the curl is not 0, then this technique is not possible. There can be no associated scalar or potential energy function. Now, fortunately, most of the forces we're interested in are conservative. Electricity, magnetism, and gravitation are all good examples. So, hopefully that discussion will help you understand the importance of the curl operation when working with vector fields. And with that, we'll conclude the video with a short recap. We started by defining an operation known as the curl. We defined it this way. It is the covariant derivative of a vector uk combined with our Levi-Civita symbol like this to produce a new vector v. Now, as with any first-rank tensor like this that is a contravariant vector component, we can lower the indexes and swap the dummy indexes to represent it either as a contravariant component or a covariant component. And then we can use either form along with the appropriate basis vector to form a linear combination and thus an invariant form of the vector. We also showed that the notation for the curl in general literature is either to simply designate it as the curl of U or to show it in dyadic form this way. And we do it like this because the curl definition very closely resembles that of the cross product. We then went on to derive an alternate form, showing that this form of the definition of the curl is equivalent to this one, and that this form is much easier to use when it comes to actually evaluating it in each of our coordinate systems. We also use this alternate definition to derive a couple of important identities. The first is that the curl of the gradient is equal to 0. also expressed in dyadic form this way. And the other one was that the divergence of the curl, expressed this way in dyadic form, is also 0. Now, this identity is particularly important because we demonstrated that it is the test to show if a force is conservative. And if the curl of our vector field is 0, then that means we can represent the force field as the gradient of an underlying scalar field or a potential function field. And that shows us why the curl operation is a very important tool when it comes to working with vector fields. In the next video, we'll move on to the topic of integration.